Happy Tuesday here. Got everything set up now, I think, on this laptop. Sorry about that. Last time around, Visual Studio and Visual Studio Code. I don't understand why they picked the name, but okay. Microsoft does fun things like that sometimes. So got the right tools installed on the back of the laptop. I still haven't even mailed it in. I got to go to the FedEx store. I'm like, I don't really want to drive to a FedEx store. So hopefully maybe on the way back today, I can stop and mail my old one, get that repaired. So back to the nice laptop. This one is slow, which is sad, but it's okay. So we need to talk about stacks and queues here. Searching and sorting we can get to on the third. Not too worried about that. We should be in pretty good shape. That okay? So we'll talk about stacks and queues today, and then we'll talk about searching and sorting on the third. I think we'll be all back up to date here. But I've been told, apparently, we learn better by writing. So I think instead of writing code on my computer, I'm just going to use the blackboard here. I'll write all the code up on the blackboard. Does that sound good? It's April Fool's Day. I'm trying here. I'm sorry. I started back in 2016, and I had one of the guys, he's a really nice guy here, but he would give his tests on paper, and half the test was writing code on paper. And he's like, oh, if they know it well enough, they can write it on paper. And it's like, and he would mark them down if they didn't have semicolons and curly braces. It's like, no, the tool does that for you. Like, that's not the kind of thing you need your mental head space for. He's like, no, they can do it on paper. They've been doing it for 20 years on paper. It's like, yeah, but we don't have to anymore. So I don't know. But thankfully, I don't do that. I have no control over what other faculty members do for their tests. So, but we don't do that because that's dumb. So we've gotten our nice tools. We're going to use our tools. And I'm assuming, whether or not there's a semicolon is not the end of the world if you write something down. So, but some companies still do whiteboard interviews, which are terrible, and everyone knows they're terrible. And people admit they're terrible when they still do them because I don't know why. But not everyone does. We're hopefully getting away from that in the industry and not being so terrible here. Like, write an algorithm on a board. So can you communicate an idea with pseudocode, I think is useful. Like, can I give you, hey, here's the steps of an algorithm here, and sketch it out and communicate this process and design with someone? Yes, that's good. We want to have communication skills. That's why we have all of the other supporting classes here. You go to school to get a degree in computer science. You also take communication and English and these sorts of things here to learn all those other soft skills that go into it here. It's not useful if you're a genius coder but can't talk to people. It's not going to work well for you here. You have to be able to work with the team, which is nice. And it's much more fun to work on a team too. All right, so I got a project started. I actually wanted to make sure it ran first here. So I've got this one here. I don't need that. How do I turn this view off here? Oh, goodness, this is options. This layout should have imported for me here, but it's not. Oh, because I'm not signed in, that's why. There we go. Once I sign in, I can sync my layout, and it'll look back like I'm used to here. Continue. Let me get logged in here, and it should fix it for me. I think it wants to do all the new Copilot things too. I'm like, I don't. It's fun, it's good stuff, but I don't need it right now. Is that going to work? That's fine. We can just get into stacks and queues. So the idea with a stack and a queue, I've got it on the screen right. Oh, good. Is that we're limiting what you can do with this data. Now, it seems a little bit silly here, but when we're solving problems, we have different tools in our toolkit that allow us to solve them differently, right? Not everything you're going to run into needs a hammer, because not everything's a nail. So we're going to look at different ways of storing data, working with data, interacting with data, and a stack is a sort of structure in which the only thing you do with the stack is you put something on the top, you take the thing off the top, or you could look at what's on top. So it's a very limited way of dealing with data here, but it turns out it's a useful thing for a lot of problems. Not all problems, but a lot of problems you can use a stack to solve things, and it works out very nicely. And what it does is it forces people into interacting with the data in the manner that we want them to, which is the stack. So if you have a vector, you can get at stuff at the front, you can get at stuff at the back, you can get at stuff in the middle, you can add stuff to the front, you can add stuff to the back, and we know it's really slow to add stuff to the front because you have to bump end things over to make room for that item. So it's slow if they use it in that manner. So if the only thing they need to do with this is interact with stuff by putting it on the top of the stack, working what's on top of the stack, great, we're good to go. So we can limit the API, we limit what they can interact with, to get better performance out here, and that helps us solve our problem. So we can write a class for stack. Should I put it in? I'll put it in its own file here. Let me go add another header. Oh goodness, what did I do here? Another header file. So we'll add a stack.h, and we'll have our class for stack. We'll have a private section, we'll have a public section here. Now, behind the scenes, we're actually going to use a vector here because this will just make our life easy. We could do this with an array and resize it and keep a bunch of nulls and nones and around. That's just a big hassle here. So we're going to take advantage of vector. So we're going to include vector here. We'll use our namespace standard. So a private storage here, and now stack is going to be of a given type here. So this will be a template class here of type name t. So it's a templated class that can hold any key thing we want to give it here. And we looked at using templates, and that's why we start talking about templates. So I can make a stack of integers, I can make a stack of floats, I can make a stack of strings, I can make a stack of the student class. And we can make classes and put them into the stack. Whatever t we give it is the t that we have. So we're going to have a vector of type t here for my items here. I'll have this internally private wrapper here, but I'm not going to give them full access to it here. So I'll make a stack constructor that doesn't need anything here, so it makes items is a vector of t here. And now I've got items, right? It exists. I'm going to go ahead and add items to it here. And then things that we do with a stack is you can push something onto a stack. So you push an item on that takes our items, and we're just going to push back that item. Okay, just add it to that vector of items. You can then pop an item off here that will give you back the last item. So that's going to take our items, and we're going to use pop back here, and we're just going to return that one here. So the vector itself can already give me the last item here. So we're just going to use that one. Whatever's at the end here, give that to me. If you want to add something to it, it goes to the end. So if we're only working adding to the end and taking from the end, we're a stack here. And the other thing you can do is you can peek here. This is a void, and then a t peek. You can also look at what's on top of the stack. This is items. Now we want the index of, right, the items.length or .size -1. So whatever's at the end here, right, the size, there is no index at size, but there's the last item is at size -1. We start counting at 0 like all normal people do, 0, 1, 2, 3, 4, 5. So we'll just show you, here's the last thing here. We'll just give you back that item. So this is our stack here. So we can add things to it. We can take things off, right, by pushing and popping. We can also look at what's on top here. Now, so other things you might want to be able to do here, you might have it like is empty, and this returns the items.size equals 0. Right? Or this one even has an empty? Empty. Yeah, items.empty. Nope, that does empty it out. Is empty. I don't. Okay, it doesn't have it here. Items.size is 0. So if we have no items, we're empty. So this sort of way we can like loop through our stack. As long as we're not empty, we can do something with the stack. Just gives us a quick way to be able to interact with it. And in terms of performance here for these things, how fast do these things go? Remember, we wanted to talk about these generally the time complexity, how fast it is in terms of how many n items I have. So if I have n number of items in a vector, how long does it take to add something to the end? Right, on average, right? So our average O performance is going to be constant, right? Because eventually it has to do that resizing. I think we looked at that a while back, right? When we looked at our dynamic arrays versus vectors. Eventually you have to make room, but on average, we get to do our fancy hand-waving math and say the amortized average is constant, because most of the time it's super fast, and when we do have to double, we're able to do that at this geometric doubling pace so that we still average it out to a constant time here. So our average speed for pushing is super fast, which is nice, right? You know, the worst case is O of n, which is unfortunate here because you do have to do some doubling, right? Occasionally you have to double your storage, but that doesn't happen very often here, right? And then to pop something, to remove something off the end here, right? Just taking the last item out of a vector, nothing has to shift, nothing has to resize here. Now, eventually you want vectors to be small enough. So if you add 1,000 things and you take out 900, you don't need to keep room for 1,000 things. So eventually behind the scenes, C++ will do some resizing here. So it does have a worst case of O of n, because occasionally you have to shrink your storage, so we're not oversized. But again, on average, it works out really nicely for us here. And then peak then is always an O of 1 operation here, a constant time operation, because we know exactly by index, we can get to that location by index and go read it. Here's the value, always O of n. Best, worst, average, all the time. Always O of n for everything here. And then is empty is an O of 1 operation. We're just checking the size here. We don't have to count anything. We don't have to loop through add items. We just get those items. So this works out super fast for us, which is really nice. So if I want to include our stack here, include stack class here. I want stack.h because we wrote our own stack here. So I can make a stack here. Stack. Here we go. Stack. Is it not? Oh, stack of, that's right, type, how about int here? Stack of int. For a stack here, we can add a bunch of integers to it, right? Stack.push, we can add, a 10 and a 20 and a 30 and whatever we want here. 10, 20, 30. And then while my stack is empty, well, it's not is empty, right? So it's not empty. Here we'll see out stack.pop. Let's take those values back off here with an end line here. So we're going to get in reverse order. And if I put a 10 on first, that's what we're going to get last. So it's a first in, last out, or a last in, first out kind of thing. So we should be able to get out a 30, 20, 10. If we did this, oh goodness, build errors. I'm missing a, where? What the heck? Oh, missing a semicolon. See, we want the IDE for this sort of thing here. Really? More build errors? Cannot convert void. Where? Items pop back. Oh, that just removes it. Shoot. Okay, so pop back doesn't actually return the value here, right? That's just giving you back a void here. So I need to get this item here. T item equals this one here. Then call pop back here to remove the last thing, and then I can return the item. So I thought vectors were nicer than that here. So grab the last thing, remove the last thing, and then return the last thing. Right? And 30, 20, 10. Hey, it works. Okay, we're happy. So this is working well for us. I don't need hello world here. Okay, so I can put things on, take these off, look at items here. It's a very limited view of what we're doing, right? But turns out, remember when we did the recursion, we looked at our stack trace, or we looked at our call stack? But behind the scenes, it actually uses stacks, like in when our code works, which is really cool. So if I put a breakpoint in here, we can see the call stack is actually a stack structure here that C++ uses while our code is running, right? Hey, we were at line 16 of main, then we went to line 25 of pop here, and this one, hey, goes and calls vector at, so if I want to step into, where's all my buttons? Oh no, I have too many toolbars here. Where's my stupid debug? Step, all right, sure, I can use this one, step into. Oh, it's not even doing that. Okay, that's fine. I wanted to step into vector, but I guess it's not going to step into vector for me here. Step into, wanted to see another call in the call stack, but you've seen it, right? You can get, hey, here's the next function, here's the next function, here's the next function, all the way through. That's a stack, right? And we work them from top to bottom. You can't get to the thing underneath until you're done with the function we're currently in. Right? When that one's done, we come back. So that's all. I don't even have the stop button. Wow, I have way too many toolbars here. Add remove buttons. Can I just turn them off? This is not a widescreen laptop, and I'm sad about it here. That's fine. We'll just stop. Don't need those ones. Okay, cool. That's our stack. This one's pretty basic. It works really fast, which is nice. Now the queue is what you're familiar with in English, or in American English, we call it a line. British English, the Queen English, it's still a queue, right? The first person in front gets served first. You show up at the end, right? You add to the end of the line here. So we call it a line, we call it a queue, which is fun. And it's also fun when you think about the word queue, which letters are silent in queue, right? Is it a silent UE? Is it a silent UE? Like, it's just the letter Q at the front, or is it QUE? Which one is actually silent here? It's fun. All right, so this is a class for Q. It has a private section and a public section. And again, this is a templated class, right? So it's a template of type name T here. So whatever T type you want, we can make a Q of that given type. Now, there's a couple ways to do this. And we're going to look at the bad way first because it's illustrative here. And then we'll look at a better way to do it, which is still not the best way to do it. And then we'll look at the best way to do it. Does that sound okay? All right. Which is a bit tedious, but it is worth it, for the sake of the exercise here. So let's use a vector again here. So we'll include vector. Include with a pound sign. And I tell you, this is an octothorpe is the technical term for this. If you like being pedantic, you can tell people that's an octothorpe. I call it the pound sign. It's only a hashtag when it touches a word, right? Have I gone off on a crazy rant about that because I'm weird? Right? All by itself is just the pound sign. Right? When you attach it to a word, then it becomes a hashtag because it includes the word that you're including, right? Otherwise, it's just the hash symbol, right? Okay. Anyway, arguing with people for the sake of arguing is lots of fun, right? That's all why we're at college. So we can argue with people and tell them how smart we are. I try not to argue with people on Facebook because I know it's pointless here. But some lady was going nuts here about crazy things, and she told me that I should go do my own research and look it up using ChatGPT because it will tell me things that Google will not. And I about died. Like, I generally don't throw out the fact in arguments that I teach computer science and I'm a prof at relatively well-respected school, right? But to tell me that ChatGPT will give me information that Google will not, like, lady, these tools just make crap up, right? They hallucinate. They don't give you real information here, and like, just wanted none of it. She's like, no, Google's just hiding that from you. They're hiding the truth from you. Like, oh my goodness. This was just some crazy lady on Facebook. They were not a student. Yeah. I know a thing or two about how these tools work. I've not written my own here. I'm not that smart, but I know how they work, and they make stuff up. And she's like, no, they're just hiding information from you on Google. The big tech companies are censoring things. And she's like, you must be one of those deep state actors here who's like subverting our children at university. Like,
we've been to a hackathon last weekend in Oakland, and I was not as familiar with Flash. So I was like started coding, and we needed a single line of code, which I was like managing to do 10 or 15 lines of code to connect the camera to the computer, and I used GPT and helped me to gather it.
Oh yeah, it's great to come up with code examples, these sorts of things for sure.
So of course, if I use it to write the full code, it would probably mess me up.
You just have to vibe code your project, right? I don't know. I feel bad trashing out it all the time, but it's throwaway code. It's not good enterprise production code that we're going to maintain for years and years and years and years. Like, it's sad. I sent I gotta find it here. It was I sent it in WhatsApp to my buddies. It was like the meme with Michael from The Office and handshaking with somebody, and it's always like the sad funny face. And it's ChatGPT or GitHub Copilot that wrote my code, and GitHub Copilot that's reviewing my code, saying you did a good job. They're handshaking. It's really funny. We're going to need to invest in some good review tools as we get more auto-generated nonsense.
About the quiz, we don't have any specific deadline.
Just by the end here, anytime we want to get the quizzes in, it's fine.
Probably assess them.
Yeah, I'll go through and score. They should mostly auto score. I think I have to go through. There's a couple of answers that I have to go through and fix up after you put them in. I'm sorry?
Sometimes it could show like the written ones.
Yeah, those ones. If I turn on auto grading for them, the auto grade just doesn't work. Like, it's,
I started calculating my grades.
yeah, I'll punch those in later this week. When we're in lab, I'll be able to get caught up on a lot of those too.
And we don't have any lab submissions left, or?
No, we still have lab. We got lab tonight. We'll have lab on 4/8 and probably 4:15. We'll do our ethics lab, but that'll be really short.
So this week we don't have any lab?
We have lab. Yeah, lab tonight, lab 4/8, lab 4:15.
Okay.
Yep.
Do we have any submissions?
I'm not sure what you mean by submissions.
Like,
We'll have a new lab assignment.
Yeah.
Yeah, we'll have 3 more lab assignments.
Okay.
Yep, and that'll be then in the labs. 4:15 will be a short one, just on ethics. Yeah.
Sorry, I have a lot of questions.
That's okay.
Group project. The thing is, can we work in pairs?
Yeah, pairs. So you don't have to work as a partner with a partner. It's not a required outcome here
Yeah.
of these things, but ideally you work with a partner. There's not enough work for a group of three. If we want to work in pairs, great. If you want to do it by yourself, you're welcome to do it by yourself. You'll get to group projects eventually here in school.
And it's a three exactly at the same date and time I have the final exam on the other subject. So
It shouldn't have happened the way we scheduled things, but because it's based off of when classes meet now, unless I picked the date wrong.
I do have
Wait, look it up.
formula and statistics exam. Oh no, it's good. It's good. It's still three.
Okay, yeah. So is it maybe we're starting at? I think we start at 3, right? Where's the?
Yeah, it's 2:45.
No, that's fall. I don't want. It's the bad link here. This one, registration dates.
You want to find the exam dates?
Yeah,
Yeah, it should be yeah, final exams.
didn't have the list. Here's this one.
Just go to the website.
Scheduling.
Yeah.
It's
Top right corner, you just type final
exam schedule. I almost never use these internal searches because they suck, but apparently this one works.
Yes.
Printable for it's calendar. Scheduling final exams. That's for fall. I found it earlier because I found the date in the schedule here. Why is this not working for us here? Final exam schedule. Oh, here it is. Final exam schedule. I just had to scroll down on this page. That's what it was here. So it should be based off of.
The code.
Yeah. So our class meets right. We're a Tuesday. 3:30 class, so we should be code O, right? So we should meet for Tuesday the 24th. Yeah, 3 to 6. Yep. So hopefully we don't have any conflict. Occasionally it happens with online classes, but let me know. But yeah, so the idea is you can plug into the HDMI port, or I can pull your code on my laptop.
And then we just explain the code.
You just run it, show us the output. I might have a question or two about it. The Peanut Gallery might have a question or two about it. It's 5 minutes or less per presentation, 10 if you really want to talk a lot here. Most people don't. Yeah, it goes relatively quick here, but we do have a pretty full class still with people who need to present. So yeah, preferably with a partner. If not, that's okay. What? I mean, it's actually, there's more work involved because you have to coordinate with each other. So like, it's not actually much less work to work with a partner, but it's a better experience. I think you get better results typically working with a partner. Yeah. Yeah, definitely. Yep. So we've got those, and then I need to give you if you're working with a partner, I've got a review you can use to review each other, but not everyone's doing it. So, but I've got a fun little review I stole from somebody. I forget who it was years ago, and I've been using it ever since. Here, some school put this group eval out here, which is nice. So if you're working with a partner, you can do the group eval here. If not, it's okay. You don't have to. But this is nice. You rate people across a couple different categories, right? Your quality of work, problem-solving skills, teamwork, initiative, communication, time management. And I hate to burst your bubble, but being average is okay, right? You all understand math here. We're probably on a bell curve here for talent. Most people are going to be within a standard deviation of the mean. That's okay to be average, right? Not everybody's going to be exceptional. I really hate when groups turn in evals are like, everybody's a 5 across the board. I'm like, no, they're not. Right? You're not going to have a group where everybody's exceptional. It's not going to happen. Let's be honest here, right? It's an average for a reason. So don't feel bad to rate someone an average. That's really okay, right? Occasionally they're good, right? Rarely they're exceptional. Right? So averages are fine here. And this is a good chance to reflect on, hey, how was I? Maybe your partner sucked at time management. You can tell them they did a poor job of time management. Don't get offended here. That's a chance to like reflect and be like, oh, maybe I could do better as a partner next time. Eventually you'll get to your senior design project where it's a year-long, 2-semester-long, 10,000-hour project here. I don't know if 10,000 is right, but I think it's about 10,000-hour project, which is a significant project you can put on your resume and talk about. And this is one of the selling points of our program here. You've done something unique here. And that's someone comes in and pitches an idea for a project and your team works on it for 2 semesters. You got all sorts of cool deliverables, all sorts of cool things you can talk about. That's a unique project. It's not the, hey, I did a traveling salesman algorithm that literally everybody does in their algorithms class. I don't care. No one needs to put traveling salesman algorithm on their resume. But I was just immediately flagged. They have nothing better to put on here. We would throw it out when we were interviewing people because everybody did it. Right? It's not a unique, interesting thing to talk about. So our senior design capstone is really cool for that, which is really fun. So we'll do that. Yeah, rate each other. Average is okay. Right? Don't feel bad to rate someone average. So I put that one out there. I'll put a note in there as well. If you're working with a partner, do that. You can even review yourself. Take a minute, do a little self-reflection. If you did it by yourself is good. Here, tell me how you did for that. So back to Qs, right? So if we have our Q and we have a vector of type T here, now with the Q, right, here's our data or items, right? Again here, items is pretty easy. We'll make our constructor for Q. That actually creates this instance of Q here. So my items is a vector of type T here. And now with a Q, you can enqueue an item. So it's a void function to add something, right? You add to the line here, a T item. All we're going to do is add it to the end of the vector. So we'll take our items, we'll push it back, the item, right? Sure, I can add to the end. Done. Now, no matter how many items I have, again, this should be on average here, O of n, or O of 1 operation, because averaging that across, we don't have to double all the time. This is usually pretty fast here. The other things we do then is we can dequeue an item. Here we can take from the front here. Now dequeue with a vector is going to be really slow because I have to go get the thing at front here. So here's my T item, is my items at 0. Right? Always the first thing, nice and easy to find. But now I have to remove that front thing, and n things have to shift down to take up its space. Right? This is going to be terribly slow to go remove that item here. So I can get the items, what front is my items dot the iterator here. It's auto front items dot, come on, auto complete for me here, items dot. Why do I not get type ahead? Really? I broke my vector. Items dot. No members of, what do you mean no members available? Right, get rid of this line, stop confusing it. Items dot. Telesense isn't working. All right, maybe this is why we don't need to rely on our tools so much. It's like front, isn't it? Do you remember we were doing our iterators? The front iterator? Why did it break? All right, can we just build? Just build for a second. Let's see if I can shake it loose here. Items dot. Really? Error type? We didn't use the namespace. Using namespace standard. Now it's going to work for me. Items dot. There we go. Hey. Okay. Beginning. Right. Here's the front iterator here. So here's my auto type for the front. Is items begin here. Right. Give me the very first thing at the front. Then to go remove from it. Items dot remove. What was it here? Is it delete? Erase. Erase says, okay, where are we erasing here? What's the iterator here? So I'm going to erase the front here from it, and then I can return the item. Right? Get rid of that front item here, and then give it back. So here's the front thing. Now this is where it's slow, right? Erasing the front thing means I have to shift over as many things that are behind it back into the front place here. Right? And then the thing goes in the first index needs to move, and the thing for the second needs to move, and the thing for the third that needs to move. So this then is always O of n here. O of n operations, which is bad, right? That's slow. We don't want to be slow, but it is for our purposes here. And then a T front, if you just look at the front thing to just return this item, here's really fast. We can just say, hey, here's what was in the front, but not remove it here, is much faster, right? So again, this gets to be slow for us here. We're not going to notice it's slow because computers are fast until we've added like 10,000 things here, but eventually it will slow down for us here. So maybe we can say, let's include Q, include Q, H, and then let's make a Q, Q, Q.
I don't think it was included right.
Query? Oh my goodness. Q.H. I should have just named it with just the letter Q, right? How's it gonna work for me? Q. Really? Did I spell it wrong?
No, because the type maybe.
It's type. Thank you. Q of ints. Sure. Ints. Thank you. All right. Now let's make a bunch. So I don't know. For int number 0, number is less than. Let's do I don't know, like 100,000 things. Number plus plus. Let's take our Q. We'll NQ a number. Now this should be fast-ish. Right? It'll have to double occasionally here, but this should be pretty quick. But now if we do our isEmpty, let's go copy that isEmpty method again here. Say, hey, as long as we're not empty, let's go DQ something. And while my not Q is empty here, let's see out the Q dot DQ and then line. Now we should notice that it's getting relatively slow, but it should be in order, right? When I added 1 to 100,000, we should get back out 1 to 100,000 because first in, first out, right? Usual for a line. But it should be relatively slow for us here. Let's see if it acts kind of slow. Oh, we don't need debugging here. Let's continue. Hey, look at that. It's going kind of slow. Not super slow. But yeah, or maybe it's the output that's slow here. We're not actually seeing the queue itself be very slow, are we? But eventually it'll be slow. You know, if we get enough items, maybe we have to shift, you know, maybe 1 million things or something, we'll notice it being a little bit slow. Again, computers can do 1 million things relatively quick, but slow is bad, right? And if we're trying to optimize things, then this is not good for us here. So can we do better? I'm so glad you asked. We can do better. Yes, amazing. Who knew we could do better? So one way that we can do better here is we can just not actually remove things here, right? So what we can do here, let's actually copy this one here. So we'll call this how about we call this one a slow queue here. The rename here, call this slow queue. This is my slow queue. Let me go add another class here then to this file. And let's have this be a faster queue. So to be a faster queue, what we need to track is where the actual first item is. So I'm going to have an int for the front index here. So when I start, then my front index will be, actually it's like -1 to really start. And then every time I add something now, I can take my front index plus plus. Right? So every time I add something, let's add to it. So when I add my very first thing, it's now 0, and then 1 and 2 and 3 and on and on and on. So we'll start it at -1. Now when I want to DQ something, it's not the items at 0, it's the item at the front index here. Right? And actually, I'm sorry, when I NQ, I don't add to that one here. Shoot. What do I want here? So I'm only moving front index when I DQ something here. Shoot. So maybe we can probably start at 0 here. If you DQ and you're empty, you just screwed up, and we just won't worry about it right now. To do fix DQ when empty. All right, that's okay. I can check real quick. Hey, if is empty, we can throw a new. What do we have to include our exceptions or something here? Include standard exception. I feel bad leaving it ugly. So we can throw a new invalid argument. Sure, invalid argument. I don't particularly care which one we're throwing here. All right. Why is my coloring all off here? I should have the green Q here, shouldn't I? Visual Studio is just really off today. That's okay. So when it's 0, right? The front is 0. Great. We'll take front index. Now every time we DQ something, I'm going to take front index plus plus. So the first time I DQ something, I'm giving them 0. The next time I'm giving them 1. The next time I'm giving them 2. The next time I'm giving them 3. On and on and on and on. Right? So I'm never removing anything here. I'm just incrementing where I'm looking here. Right? So eventually, we'll run out of things here. So we probably also need to check if we're not empty here. This is never even really going to work for us now with this one, because we're never changing size once I start removing things here. So really I need to say, hey, does my number of items here, or front index, my front index, is it greater than my items dot size here? So if I have 3 things, I've added 3 things, my size should be 3, This should be greater than or equal to, right? So the first time I DQ something, I'll give you index 0. My size is still 3. The next time I DQ something, I'm giving you 1. My size is still 3. The next time I DQ something, my size was, front index was 2, but then it moved up to 3. So now I'm officially empty until I go add more items. So if I add a fourth thing here, then my size is 4, but my front index is 3. There's something there, I'm good, right? So we just kind of change how it is empty. So what we're doing is we're sacrificing, this needs to be at the front index now. Here we're sacrificing space, right? The memory usage. So I'm never going to give up that memory here to make my queue faster, right? And this works, right? This will be a faster queue here. But turns out we can even do better than this, right? I'm so glad you asked. Yes, we can do better here. So this should work. We should test it out real quick. Let's try a fast queue here. Fast queue. Right? Didn't I call it fast queue? Faster queue. There we go. Faster queue. That's why I had the constructor wrong. So faster queue. Let's call this one a faster queue. So this one should work, but we're never resizing. But again, it's going to, oh goodness, what do we, invalid argument, empty. Do I have to give it something? I think I have to give it something. There we go. So sure, now it spits out. Again, it's a little slow just because output is a little bit slow, but we can get our queue filled up and use it. So it seems to work okay, right? Maybe we try just 10 things, right? Make sure we don't blow up with 10 things. Should be able to get out 10 items. Uh-oh. 0, 2, 4, 6, 8. I think we missed some items here. Oh, I was not changing my NQ, DQ. No? Front index. Oh, we were still erasing. Oops, we don't actually erase anything ever. My bad. Sorry. There we go. Don't actually erase anything. We were erasing with the faster one. Now I get my 1, 2, okay. Now we get all the numbers out we expect. So faster here, but we're trading off memory, so we can do better here. So let's do better. So we can do better by reusing that empty space here. Now this gets to be a little bit awkward here, but it's okay. So we're going to make a circular queue. So a circular queue says, okay, if I were to have room for 10 things, and I put 5 things in, right? 1, 2, 3, 4, 5. I've got 5 things in. I take a couple things off here, and I add a couple more things, and I take a couple things off and add a couple things. Instead of doubling here, saying, oh, I've got empty space back at the beginning, so instead of going from 9 and doubling here, let me just go back over to the beginning and put the next thing at 0, the next thing at 1, the next thing at 2. So we say, hey, the front is at 7, and the back is at 3. And now when I take something off, I'll move front, move front, move front. Hey, I got to the end, start back at 0. So I'm going to reuse that empty space here then. So we'll have a front index, we'll have an int for back index. So we'll start at 0 and 0. Back index is 0 here. And then every time I add something, I need to change my back index here. So if I have room in my vector, I can change where I'm putting it then. So when I add the I'm not pushing it back here. I'm going to resize this thing here. This gets to be a little bit messy, but I'm going to add like 10 nothings, essentially. So I can add, we probably want like null pointers here, but that's going to be really messy here. So we can say, hey, make this of size 10 here. So I've got room for 10. And then put in 10 nothings. Ugh, this is going to be really ugly here. I don't want to have to write all of this here. We need to change this to circular queue too. So we'll essentially put in 10 nulls here. So I don't know, for int index is 0, index is less than 10, index plus plus. We'll take our items at 0 and we'll assign it the value of, give it a null pointer? I think I can give it a null pointer. That might crash on me here, we'll see. And then we have no front, we have no back because we're empty. So when I add something, instead of pushing back, I'm going to see if there's room. So if there's room here, then my front and back index aren't the same because I've got some empty space here. Only works if they're not zeros though, shoot. So I want to make sure that I have room. We'll check. Okay, so we'll say, hey, if my number of items is less than my items dot size. So if there's actually room here, then I can go do it. Otherwise, or I guess maybe I should say if it equals my item size, then we'll go resize. Resize. Make a little private helper function for resize. Then I can go add my item, so then I can take my items at the back index plus 1, right, and assign it the item. So where the last item is here, so if I have 5 items, my back index should be 4, the last item there, go add after that at index 5. Right? I know I've got room here because I haven't reached my capacity here, so I have to track number of items equals 0, so we'll add in the number of items. This is a lot of work here to reuse a little bit of memory, right? But it's okay, I promise. It'll work for us here. So make a vector, put 10 nothings here to start. So we're essentially trying to manage our own memory. It's kind of like we did with our dynamic arrays. We had to manage it ourselves. We had to double eventually here. We're doing that same sort of thing here. We're leaving a bunch of space empty here to make room, and as I use things, I'll put them in here. So enqueue, if we run out of space here, we have to go resize here. Otherwise, we can go add our item here. Once I've added my item, I'll take my back index, add to it. But it's possible now that I've added my last item and I'm out of space here, so I need to go shift that around to the beginning here. So the quick math for that, I can say, hey, we'll take back index equals back index modulus items.size. Right? And really, we can just do all that arithmetic right in one. So back index plus 1 here. I don't need to have a separate line for it. So add 1 to it, and then go modulus the size. If my size was 10, and I got to index 10, I'm going to reset back to 0. Right? This resets me here, which is really nice. So really quickly puts me back to where I need to go, always based on the size of my storage here. So for resizing then, I'm going to have a new vector of items. So this is vector of t new items equals a vector of t sized to items.size, and we'll just double it here, right, times 2. Then I need to go copy all those items out into this new vector then. So now I'm going to start at the front index, going to vector size, to start from the front to wherever I was, and I'll go from the back to the front. So then for int index starts at my front index, as long as the index is less than items.size, I'm going to take index plus plus, and let's go copy items over. So I'm going to take my new items. I need a new item index too. So new item index starts off at 0. I'll take my new items at the new item index, right? And I'll assign it the value of my items dot at the index. So wherever the front index was, hey, index 3 is now the front here. Let's put that at the beginning of new items index here. And we'll take our new item index plus plus. So go copy off from the front all the way to the end here, whatever we had, right? Then now we need to, if there was stuff at the back, so if back index was like 3, because we went from like 7 to 3, we kind of looped around here, I need to copy those last couple items here. And so for int index is 0, index is less than I guess we only have to do this if the back index is less than the front index. We should check that first, right? So if my back index is less than the front index, right? So if we've looped around, we're in a state where we've got more items at the front of the queue that we haven't processed yet, then we can go through and say, okay, for int index is 0, index is less than the back index here, index plus plus. And again, we're still using this new item index, so we'll take my new items at the new item index here equals the items at the index. And then we'll take our new item index and we'll add 1 to it. So if I've looped around, so if I was at, hey, I've got the front index is 0, the back index is 5, and I have room for 10 things, I'm just going to copy from the beginning to the end. nothing's going to happen here because my back isn't greater. But if I've looped around here, I've taken advantage of some of that earlier space in the front here, we'll go copy those ones as well, so I don't miss any here. And this will put them back in the correct order, right? Then once all of that's done, then I can say, hey, items is equal to my new items, right? Replace that vector with this new one here, right? We can get rid of that one. And then my front index is 0. My back index is then my number of items. -1, right? That should be where the last item is, right? Should be my size -1. How many? So if I had 7 items, right? I'm still have, I know from 0 to 7, my last index is 6 here. That one should work out for us here. All right, so we got our Q, we set our fronts here, our NQ at our back index +1, add 1 to back index, modulus by our size. To DQ then, again, we can check if we're empty or not, we'll take the item at our front index, we'll add 1 to front index, and we have to do that same arithmetic, right? Because front could have gone over the size here, right? To go back around to the front here, this is my front index, then add 1 to it, modulus the size here. So if you took the last thing, hey, you took index 9 and I had room for 10 things, let's circle around back to the beginning here of 0. So the front then is our front index. Now is empty isn't less than or equal to size. Is empty then is going to be when my number of items is 0. Number of items is 0. So we should take away number of items, right? Every time we DQ, we'll take our number of items -1. So every time I add something, we'll take our number of items +1. So we should be able to add or remove from it here and have it reuse that space here. Eventually it'll have to double here, right? If we add enough things, we'll double, resize our vector to be large enough to store all these things. And hopefully this one works for us now. Let's try it and see. See if we can add to a circular queue here. NQ and DQ. It might break. We'll find out. Oops. Nope. Cannot convert from a null pointer. Oh, goodness, to an int. Yeah, using these nulls is obnoxious. Shoot. Do we have to do anything? We don't even have to do anything here, actually. I think it might just size for us without the null pointers. Because I'm saying, hey, give me size 10. We'll see if it doesn't. Oh, shoot, invalid subscript. Stop. Out of range. Okay. Doesn't this size it for me of size 10? Vector. Doesn't that give me the resized vector? Constructor. I can't type, but hopefully it knows what I meant here for constructor. Yeah, look at that. Gave me the right ones. Yeah, T. The space here. Right, size. Vector. A given size. I don't actually want the beginning one, right? I just want empty, no elements, and elements, yeah. It's a fill, shoot. Resize, maybe I can use resize to 10. Let's try that. Vector items.resize 10. So then I want to make my new vector then of items.resize items.size times 2. I wonder if that'll work for us. It still crashed. Okay, where are we here then? We're NQing. What are we NQing? The number 9. Okay, so we don't have room at 10. Shoot. We're adding, we have 9 items here, but our size should be 10, so we didn't have to resize, right? But I can't get to 9 plus 1. Did we do that wrong? Just back item, what do we have in items, right? We've got 9. Why do I have 2 zeros? That seems wrong. Why do we have 2 zeros? Oh, because we never added, okay. So this, I think we just add to back index then, right? Just add to the back index. That might do it for us here. Stop and rerun it. Because when we're empty, we should add it at position 0 here, not at position 1. See if that works for us. Hey, look at that, it didn't crash. Right, should we take a couple things out, add a couple things in? So let's just do a couple here then. So we added in 10 things. So let's go and just take out 2 or 3. And then let's go add a couple more here. Oh, let's add from 11 to 20. Right, and then let's take out the rest. So we should still get them out in the right order if we did it all right. Everything but that last 0 looks good, right? Oh, no, we got out a couple extra zeros here. So we got out 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we're missing 10, 11, 12, 13. Okay, this was not good. This was close. We got close here. So let's see. So when we go, we DQ'd. Let's go and see what happens when we NQ here. The DQ was good, right? We got the correct numbers, but now we need to go add in 11. So let's step into, where's my button? Step into F11. So we've got our items, right? This has item, oh, we got to step one more. F11. Okay, so we don't have to resize, right? We're okay so far. We have 7 items left. So the back index is, why is it 0? Why did back index become 0? We never moved back index, right? Shoot. Well, it should have added +1 modulus size. If we added 10 things, do we resize? What is size here? What is items? Size is 10. NQ. Number of items. Back index. Oh no, 0 is right because we popped off the 0. This is good. It should be putting it at 0, right? Because we've already printed off those ones, right? We printed off the 0, 1, and 2. So we should be back in 0. Okay, so this is correct. That should be 0. So we go and add the item then at 0. Let's do 11. And then we add 1 to back index, modulus size. Now back index is 1, which is good. Add 1 item. We're good so far. So we NQ'd 11. To NQ 12 then, right? Puts it at index 1, which is what we want here. Good so far. Now we're going to NQ 13. That should have room, right? Because we want to overwrite the 2, right? We already popped the 2 off. Now back index here is still okay. Here number of items now is 10, and 10 should be our size, right? So now we should be resizing this next time here. So we NQ the 14, we should have to resize, right? Number of items is 10. All right, we're going into resize. Okay, so resize is where we screwed up here. So we make some new items here. Resize new items. So the new item size is 20. All right, cool, it's working out so far. Now we're starting at our front index of 3. Here, copying everything over, should be good. So we've got new items then, is all empty here. And we copy into all those spaces, right? Looking good so far. 3, 4, 5, 6, 7, 8. Oops, 8, 9. Yep, okay, good so far. But now back index was less than the front. Oh, back wasn't less than front. Because we were full. It should have been less than or equal to the front. Right? If it's equal to the front. Okay, that was hopefully was our problem here. So let's go ahead and stop. Let's give it a run again, see if it copies off. Okay. We don't need the breakpoint though. Shoot. Take that out. Continue. And where's our output? 11, 9. We don't have 10. We never added a 10, did we? Did we write to 11, 12, 13? There's no 13. 14, 15, 16. It's getting closer here. But we never added a 10, right? Because we stopped at 10, so we should have started at 10. Does that look a little better? Let's see. 10, 11. Oh, we're missing a 12, though. 13, 14, 15. It's close. So we're missing one number. How are we missing a 12? So somewhere with that circle, we're missing it here. Let's go back and debug here. Because we know we're missing 12, right? That's when we started resizing, right? So I think somewhere in resize is still probably the wrong bit here. So let's put our breakpoint in resize here. Let's continue on. Continue the way resize. Okay, so we're ready to resize. So we've got this has the 12, but somewhere we're missing the 12. Where items index is less than or equal to the back index. We need to get to back index. Okay. Hopefully that was it then. Now we can take that breakpoint out. Let's see. Did we successfully copy that one? Nope. Still missing the 12. All right, we were closer though. Put our breakpoint back in here. All right, so we're resizing here. Let's go. We've got our current items, right? 10, 11, 12, 3, 4, 5, 6, 7, 8, 9. So we should copy new items then, right? Copy over into new items. We should have 3, 4, 5, 6, 7, 8, 9. That should be it. Now we're saying, okay, now let's copy the back index here. So now starting at 0, go back to the back index less than or equal to 3. Let's take new items at the new item index of 7. That should be my new items, right? Index of 7, right? So we're going to copy over items at the index of 0. Here's the 10. Now copy over indexes 1, copy over the 11. Index is less than back index, right? Copy over my index again, right? Index then is 2. Copied over the 12. We had the 12, okay. Copy over more things, right? Back index is 3. What do we put in here now? We went too far, so this was too far. That didn't work for us. New items. I think we went, because yeah, back index, this is one further than we actually have for the back index. So it was too far. But now why are we getting the wrong one? My back index is my number of items -1. Is that incorrect then? My back index should be 10 minus 1 should be 9. When I add things, I'm adding them. Where am I adding them? Here, I'm adding it at the, so I'm overwriting my last item here. So my math isn't working out here. So this should just be number of items then for my back index, right? Because we were said before we were putting it in where the last one was, there wasn't anything at back index. So we had the wrong number there. Let's try that one more time here. Hopefully now we get all the right numbers out. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I think it worked. All right. Got through all of our bugs. We love the debugger. If nothing else, spend time debugging things. I promise it will be worth your time. You want to be familiar with debugging things. Helps out a ton here. Now, this is still occasionally slow, right, because it has to do the resizing, right? So average of 1 still, but worst case, we still have to resize. So can we do better than this? Well, thanks for asking. Yes, we can if we use linked objects. Right? A linked list here, you can add to the front, add to the back, constant time. You can remove from the front, remove from the back, constant time. Remember we did linked lists? So if we use a linked list to store this, adding to the end, always instant, adding to the front, always instant, or removing from the front, always instant. I just say, hey, the front thing is now here. Right? The back node is now the back one. So we can do this super fast with linked nodes. We'll do that one last time here with a class for linked queue. So we'll call this one our linked queue. Now we don't need a vector now, right, for this one here. We're going to have an inner class here. We don't even need a front index or back end. We have a front and we have a back, like node here, right, front node and back node. And I still want to know my number of items. This is probably useful here, maybe here. We never need to resize here, which is super nice. We get rid of a lot of code there. No big headaches here. We don't need vectors, right? We would make one. My front node is a null pointer, which is technically 0, which is fun, but that's okay. Back node is a null pointer here. 0 items. So we need that private node class, right? This inner class for node. So write another class for node. Then of type T, right? This is a template of type name T here. So a node then has really all we really care about is this public section here. We don't need any private values. This is just this inner working class here. So we'll have a T or node of type T, right, for the next. We'll have a node of type T for the previous, and we'll have the T data, right? And we'll make a constructor of node of T, a constructor then that takes a T data, and it takes a T node of T T next. We'll assume is a null pointer until you tell me otherwise, and it takes a node of type T previous, which we'll assume is a null pointer until you tell me otherwise. Right? So then my this next is the next, my this previous is the previous, if I can spell that right, and my this data is the data. Right? Back to linked lists. Remember, we don't going to forget these things. We're still going to use them here. So then null pointers for those, when I went NQ something, again, we could use the circular. Do we do a circular linked list? Those would be nice. Don't need to worry too much about it here. So we'd never have to resize. To NQ, we just always add to back. Right? So the only thing we have to worry about is if my back node is a null pointer, then my back node equals a new node of T given, now if I had nothing, I don't have a next, I don't have a previous, their null is fine here. So I just have to give it the item here in my data. And then also now my front node equals the back node, right? Because the front is the back if I was empty to NQ something. Otherwise, then I just add a new back node, right? So if it wasn't null, I have one that exists. So I'm going to make a new node. So my new node of type T here, new back, then equals a new node of type T given the data, and then its next is null, which is fine, but its previous then, next is a null pointer. Its previous then is going to be the old back node. Right? I have a new back node, and then my back node can equal the new back. Right? Add it in. Nothing comes after it because it's the back here. This thing comes before it. I can NQ pretty quickly here. And then to DQ something, again, we could check all these things. We don't have to do most of that stuff here. We're going to take the T item, then is my front node dot data. Right? Grab the data out of the front node here. Right? We know what it's pointed at here. It's got its data. And then we just move the front node to the next one here. So my front node then equals the front node's next. Maybe want to check to see if we're not empty, but that's okay. So we can return the front node's data. Front here is empty. Number of items is 0. Sure. Oh, we should probably remove an item then, right? So my number of items minus minus, number of items plus plus, number of items plus plus. Front node. Oh, those aren't its here. There we go. Node of type T. Node of type T here. There. Now those hopefully light up a little bit nicer here, right? You get nodes here, the linked queue, Okay, now all my colors are lighting up here once I fix my errors here. So this one then, because we're using linked objects, never has any resizing. So it's always O of 1 here. It never has to do the resizing. It's very, very fast all the time here. DQ, O of 1 all the time, right? Because we never have to do any of that. We should have fixed some of these before here, right? The DQ then with a circular is O of 1, right? On average, because we're just removing, occasionally in the worst case it has to resize here, but it's always going to be better. And for this one is also a 1 for the DQ, right? Because we're just using space here with our faster one. Here we go, I had to fix those. So this one should work for us then using nodes. We never needed to know the difference, right? Using the queue on this side, we didn't care what kind of queue it was. It had the same API. You could NQ, you could DQ, you could get the front, right? The same public methods here, same public functions, the implementation details we hid. That's the idea with abstraction. You don't need to know the details of how it works. Now, we care how fast it is here. We want to know that it's fast, but that's for us to fix if it's slow, right? That's an implementation detail we get a fix here. So if I use my linked queue, then that one should work for us here as well. To queue and dequeue. Oh, goodness, build errors, of course. Uses a linked of int, which is being defined, node of t next, node of t previous. Oh goodness, what is it here? Just being defined. Where is it complaining now? Node linked queue int, node of int is not allowed. Is it not? I'm missing something here, aren't I? I don't know what I'm missing. We have to go back and look at our previous. I have to go back and look at the previous nodes. That's fine. We can do that. Look at how we did that. Linked lists. Linked lists. Linked lists. Doesn't really matter which one, right? Template type name T. Node of T pointer. There we go. T pointers. Okay. T pointers. Pointers. Does that fix it for us? How does it build? What is this one here? Operand. No conversion? What do we do wrong here? Private. Oh, the node pointers in this one as well, in the constructor. Goodness gracious. Pointers all down the path here. No? Still the same error. Line 171. Last node. Node of T pointer, node of T pointer, T pointer. Right-hand operator of type linked queue int of node T pointer. Do I need pointers for front and back here? Is that what this is? Pointers in my class? I think I need pointers in the class. Oh, it's close. It's close. Okay, different error. Must have data. T item, front node, arrow data, arrow next. Use the arrows all the way through, don't I? Okay, does that one work now? We're so close. Couldn't, oh, we got worse. It got worse. It was a new node. Convert all the argument types. Node of T. Pointer, new back. There we go. Pointers and so close, so close. This one here. Node of T. I don't need the T there, do I, right? Yeah, I don't need the T here. Okay. We are so close, friends. This is why pointers are fun, right? Node. Pointer, new back. All right, how do we do our new, yeah, node of T pointer. New node of T. All right, this is getting to be not fun very quickly here. Adding front, adding back. Back node. It's a T pointer. New node. No overload function. Convert all the argument types. 192. Node of T, given the back node. All right, I can finish debugging it later. I will fix it for you. This has quickly gotten to be not fun. I'll find out. I'm sure it's one line here somewhere for me. I'll fix that. But I think we're good with stacks and queues. So we'll come back on Thursday and we'll get into our searching and sorting, and then we'll be all caught up here. Does that sound good? All right, awesome. If you got any questions, let me know. If not, I will see you for lab. We'll do our lab tonight. Actually meet for lab. It's been a little while here. Sorry, I kept getting sick on Tuesdays. We'll do our lab, and it should be a lot of fun. See you tonight.